previous week we were discussing about laminar flow in tubes. So for that we did a couple of analysis. First of all, we did the laminar flow for the tubes. In that we know that the velocity profile is given by the relation, which you can derive from the conservation of linear momentum in the fully developed laminar steady pipe flow. And then we can calculate mean velocity from there. Uh, and then after we get the mean velocity, we can write the velocity profile in terms of mean velocity. So this is just a recap which we studied in the last class. So then we can also write the this mean velocity in terms of pressure drop, and for that we can replace the pressure gradient with the minus delta P divided by length of the pipe, and then we can get delta P in terms of mean velocity. And then after that we know that Darcy friction factor that is equal to 64 upon Reynolds number for laminar pipe flow, and then we can determine the pumping power required for that flow to occur. That is basically the product of volume flow rate and pressure drop. And volume flow rate, we all know that for a pipe flow we can determine by the product of cross sectional area into mean velocity. And then and this was the first topic we discussed about the pressure drop and pumping power, and then we did one of the numerical to calculate the pumping power for a pump, and then we discussed about Nusselt number profile for because we are discussing the heat transfer problem, so that is more relevant to topic. So we discussed about Nusselt number. So for the Nusselt number, if we do the mathematical manipulation which we did in the last class, we can determine temperature as a function of radius in terms of surface temperature, and the flux value at the pipe, and in terms of the pipe radius and the thermal conductivity of the fluid passing through this pipe. We can write it by this relation which is shown at the last of this bottom of this slide. How we came up with this equation that requires a little bit of derivation from conservation of energy principle which we discussed in the last class. And then from here we can determine the mean temperature first, and mean temperature we know that we also require velocity profile for that. So if we do the integration bit of this mean temperature, we can write it in terms of Tm is equal to Ts minus 11 by 24 Q dot S into radius of the pipe divided by the thermal conductivity of the fluid passing through the pipe. From here we can determine Nusselt number, which is Hg upon K, and we have seen that for the steady laminar fully developed flow, Nusselt number for the constant surface heat flux boundary condition, it comes out to be a constant value. And as I explained in the beginning of this lecture, that it is expected, because if we see the graph of H variation in the entrance region, the H value is higher, and then when we have got the thermally fully developed flow, after that H value is a constant value. So that's why Nusselt number value should also be a constant value. So that is what exactly we are seeing. After doing this cumbersome derivation, we can see that Nusselt number is equal to 4.36 for the constant surface heat flux boundary condition. And similarly, we can derive this for the constant surface temperature boundary condition, and it comes out to be 3.66. And then we can also derive these relations for some pipes which are not of circular cross section. So for instance, if we have got a rectangular duct or an ellipse cross section or triangular cross section, then we can do this derivation to determine the Nusselt number value at constant surface heat flux and at constant temperature, and the last column is for the friction factor, Darcy friction factor. So then afterwards we discussed that for the entrance region, if we want to calculate it, we can add something into the existing value, which is 3.66, and that is kind of an empirical correlation, and it comes out to be this one. And then we can also have the effect of that difference in viscosity due to difference in bulk mean temperature and surface temperature. Mus is the viscosity determined at the surface temperature of the cylinder or pipe, and here mu b is the bulk mean temperature, which is the average of inlet mean temperature and outlet mean temperature. Similarly, for the isothermal parallel plates, we can have in the entrance region we can have this correlation for Nusselt number. Now we are going. If there is anything which is not clear, you can ask now. Otherwise, we can do one numerical problem and then we can move on to the turbulent flow correlation. Is there any query from the last week's lecture? Okay, जी, it seems that
सर कल जो क्विज है उसमें जहाँ तक आपने पढ़ाया ये लास्ट वीक तक है.
no, the entire chapter we are going to cover today as well. I have shared the lecture slides for that. So the chapter 8, I would tell you at the end of this class. So hopefully it would be clear, more clear at that point. So just stay with the lecture at the moment. We will talk about the course for the quiz maybe later on, right? So it is the entire eight chapter. A portion of that we are going to cover today. Okay, ji. So now there is a numerical problem. Sorry. So consider the flow of oil at 20 degrees centigrade. So it means that if you see the figures here, the inlet temperature of the mean temperature of the oil is 20 degree in a 30 centimeter diameter pipe which is passing through an ice lake. Okay, and velocity is also given, that is the mean velocity. Now a 200-meter long section of the pipeline passes through icy water. So icy water of a lake which is at 0 degree centigrade. Measurement indicates that the surface temperature of the pipe is very nearly 0 degree centigrade. So it means that we can have constant temperature boundary condition for this kind of, right? So disregarding the thermal resistance of the pipe material, so it means that we are saying that the pipe material is this pipe is very thin surface pipe. So determine the temperature of the oil when the pipe leaves the lake. So first of all, we need to determine TE, right? And then we need to determine the second part is the rate of heat transfer from the oil, and the third part is the pumping power required, right? So first of all, if I take you on the whiteboard, so in this case that we have been given a pipe, sorry, so inlet temperature, which is Ti, that is given. I think the value is I think 20 degree. This length is I think it is 100 degree, 100 meter, no, 200 meter. Okay, so this is 200 meter. Then diameter radius is diameter 30 centimeter diameter. So this diameter is 30 centimeter, and then we need to determine first of all TE, which is the exit mean temperature. So, and we have got 0 degree at this pipe surface, and the boundary condition for this case is, because they have said that in the data that it can be taken as 0 degree, so it is constant surface temperature boundary condition. Right. So we know that if we want to determine TE, first of all, there is a formula for that we derived in the last class by doing the uh, conservation of energy on the differential element. So that formula was T was equal to Ts minus Ti exponent minus HAS on m dot C. Right. So in this case, we know Ts. Yes, it is given at it is 0 degree. Ti is given 20 degree centigrade. Now these parameters are not known to us, right? So we need to determine these parameters: H, As, m dot, and Cp value. Maybe for that oil, it would be so. Cp value can be seen at Ti is equal to 20 degree because T out is not known to us, so Cp is can come from there. For the H calculation, we need Nusselt number correlation. Nusselt number correlation. Right. So yes, anything you want to add? Fahad knows who was there. Maybe. Okay, it was just. Oh, okay, for the H calculation, we need Nusselt number correlation. For the AS calculation, that is the surface area of the pipe. We know that. How can we do that? AS is pi dl. So diameter is given pi into 30 centimeters, so it would be zero point 0.3 into length of the pipe is 200 meters. So we can calculate m dot. Oh, sorry, surface area. Now for the m dot is equal to rho AB. Rho we can see at 20 degree centigrade. Area is cross sectional area, so that would be equal to pi by 4d square, and we mean that velocity is given, I think, 2 meter per second in the data. So m dot is not a problem. So major issue here is how to determine h. Okay, so in order to determine h, what we need to do first? Anyone? What do we need to check? First thing we need to see is that the flow is laminar or turbulent. So that can be achieved by the calculation of Reynolds number, right? So now Reynolds number, if we calculate, then it would be rho into V mean into diameter divided by mu, right? Once we get Reynolds number, then we need to see that whether the flow is, we can take it as a fully developed flow or the entrance rigid flow. So for that we need to determine L, LT and LN. So for the LT determination, we know the formula, that is point 0. If it is laminar flow, then 0.05 into diameter into Reynolds number into Prandtl number, right? And if it is a turbulent flow, then LT is equal to 10 diameter, which we have shown. So this is for the turbulent flow, and this is for the laminar flow. This. Okay, ji. So our line of action would be, first of all, we calculate these properties: rho, Cp, mu, Prandtl number at Ti is equal to 20 degree. Ideally, it should be bulk mean temperature, which is Tb, but T is not known, so we are going to calculate at Ti at the moment, and then afterwards, this is the first step. Then second step, Reynolds number calculation. Uh, Third step, check whether flow is fully developed. by calculating entry length, thermal entry length, and then after that we can apply the number 4. We can get Nusselt number from the relevant correlation. If it is a laminar flow, then it would be a constant value, fully developed flow. If it is a flow in the entrance region, then we can choose the correlation accordingly. So let's start with the numerical solution. So here I have just explained that how to do it. So first of all, we determine the properties. So we are going to determine it at 20 degree. So rho value, K value for the fluid. Here it is kinematic viscosity, which is 901 into 10 to the power minus 6 meters K per second. Cp value is also given for the oil, and then Prandtl number, you can see it is very large value, 10,000, because it is oil, so it is very viscous flow. So that because Prandtl number is nu upon alpha, so because for the highly viscous flow, Prandtl number would be greater than 1, and for the heavy metal, Prandtl number would be less than 1. So now, once we get the properties, we can calculate the Reynolds number. If we do that, we know mean velocity 2 meter per second, diameter that is 0.3 meters. Then kinematic viscosity 901 into 10 to the power minus 6 meters square per second, and Reynolds number comes out to be 666. So it means that it is less than the critical Reynolds number for the pipe flow, which is 2300. So therefore, the flow is laminar. Now, the second thing we need to determine that whether this section of the pipe is it fully developed flow or it is the entrance region. So for that, because for the laminar case, we determine the thermal entrance length by the relation 0.05 Reynolds number, Prandtl number into diameter. So if we do that, the value of Reynolds number comes out to be equal to equal to 104 kilometer, which is of course very high value. So for our case, it is only 200 meters. So it means that the flow is in the fully developed region. So now it means that we need to choose uh, appropriate correlation. So we know that we are being given with the constant temperature boundary condition. So if we look back on this relation, because these are the relations for the entrance region. So if you look at the first formula, first correlation, it is for the constant temperature boundary condition, and it is for the entrance length. So it means that we are going to use this relation, which is Nusselt number is equal to 3166 plus this additional term, because in the entrance region the value of Nusselt number should be higher than the fully developed value, and we know that why that is the case. So if we put in the values 3.66 plus 0.065 d 30 centimeter length is 200 meter, Reynolds number is given, Prandtl number is 10,400. So Nusselt number come out to be 37.3. Now this Nusselt number is quite greater than the value of, which is for the fully developed laminar flow, which is 3.66. So it means that in the entrance region we would have more rapid heat transfer. Now from here we can calculate H, that would be equal to Nusselt number into thermal conductivity of the oil divided by diameter of the pipe. So that's what we are going to do it here. So it comes out to be 18 watt per meter square centigrade. Now once we get H, now we can use this formula uh, which we mentioned here. Just here, because now we have calculated H, the only thing which is unknown to us, that is surface area and m dot. So that is quite that we can do very easily, I am sure. So as, that is perimeter into length of the pipe, which is pi dl, and that is pi into 0.3 meter into 200 meters. So it comes out to be 188.5 meters square. Then the mass flow rate is equal to rho cross sectional area into mean velocity, which we know that, and that comes out to be, if we put in the values which is given to us, it comes out to be 125.5 kg per second. Now, aggregate temperature we can calculate from this relation. So, if we calculate it, the aggregate temperature, if we put in the values of Cp, okay, one thing is which I just wanted to tell you, that in your one of the quizzes, I gave the value in kilojoule, so you use that value as it is, but it should be used in joule. Okay, so you can see that here, if I can also write it 1.8 kilojoule, but the values need to be used in joule per kg centigrade, not in kilojoule. So if we do that, if we put in the values, the exit temperature of the oil comes out to be 19.71 degrees centigrade. So now what is happening physically? That at 20 degrees it is entering, and after 200 meter of length, only it has been dropped by kind of 19.71, so only 0.29 degrees centigrade has been dropped. So it means that the heat which is being transferred from this oil to the icy water, that is quite uh, less. So, or the temperature drop is quite low. So if we want to increase it, of course, if we can increase this exponent, then we would be able to increase this more. So it means that if we kind of increase the surface area or decrease the mass flow rate, then we would have more temperature, more heat transfer, and then this temperature will decrease more, right? So it means that if number of transfer units are increased, then the heat transfer would increase. Okay, and now we did the first part, which was the calculation of temperature. The second thing is the calculation of heat transfer rate. So for that, we know that for the constant temperature boundary condition, we can use the relation which is Q is equal to HAS into delta T logarithmic. And delta T logarithmic here is delta TE minus delta TI divided by log of delta T upon delta TI. Here delta TE would be equal to TS minus TE. So if I put the value 0 minus 20, it comes out to minus 20 degree. No, not 20, it should be 19.71, because T is 19.71. 19.71, so it comes out to be minus 19.71. And delta T I is equal to 0 minus 20, which is Ts minus Ti, and it is minus 20 degrees centigrade. So if I put in the values, then I can get the value of Ts, and then accordingly I can get the value of P from here. So that is, I think, they have done on this. So 20 minus 9. So we can also use it Ti minus Te, but it is better to write it in delta Te minus delta Ti. So it would be the same thing which is in the numerator, because TS would be cancelled out, and then we would be left with Ti minus Te. But as far as I am concerned, if you want to remember this formula, this form is the other easy one. Delta T minus delta Ti divided by natural log of the same ratio. Okay. So if we do that, Q is calculated, and then if you see here, Q is coming out to be negative. Why is that? Because the heat is being taken away from the pipe and it is going out to the icy water. So that's why there is a negative sign. So from your thermodynamics knowledge, you know very well that when the heat is coming into the system, then its value is positive. Otherwise, when it is going to the surroundings, then its value is negative. So that is exactly what is happening here. Okay, ji. So now the third part is the determination of. I think let me go back. The third part is the calculation of pumping power. So for the pumping power, if I show it here, for pumping power, we W of pump would be equal to volume flow rate into delta P. Now volume flow rate, we know that volume flow rate is equal to m dot upon rho. So we can also write it because why I am saying that m dot upon rho, because m dot upon rho we know from the data from part A and part B. The only thing which is not known here is that is delta P. So for the delta P calculation, we can use the formula delta P is equal to F into L upon D and into rho Vm square divided by. Now length is given 200 meter, diameter is 0.3 meter, Vm which is the mean velocity, that is 2 meter per second. Rho we have extracted from the table at 20 degree. So now the only unknown here is F. So for the F calculation for the laminar flow, that we know that is equal to 64 upon Reynolds number. So because we know the Reynolds number is 666, we can calculate F, and then other bits are other variables we already know from the data. So we can calculate delta P, which is the pressure drop, and once we get the pressure drop, we put it here to calculate the power required for the pump for to make this flow happen at this mass flow rate. So now it is just a matter of putting in the numerical values. So that is I have shown it on this slide. So first of all, we calculate the friction factor 64 upon Reynolds number. We know Reynolds number from part A, so it comes out to be 0.0961. Then we can calculate delta P by the formula I have mentioned, and here it should be rho, not mu. Okay, so which was in the slide, and it was also incorrect in the book. So please make this correction. It should be rho, not mu here. So if we do that, delta P comes out to be 1.114 kilopascal. So from here we can calculate the power required for that pump. That would be equal to 16.1 kilowatt. So m dot we know from part B calculation, or part A rather, and then rho we have determined already. So this was the numerical problem related with the laminar pipe internal flow. Now we are going to start the discussion of transitional and turbulent flow. So for the transitional and turbulent flow, for the transitional mean when flow, what is the range for that when Reynolds number is kind of less than, I think, 10,000, but it is greater than 2300, and fully developed we usually take it. This 10,000 can also be taken 4,000, but because in the book it is 10,000, so that's fine. So for that, Reynolds number would be greater than 10,000. So in this case, we would be because we cannot derive any natural number correlation from the governing physical principles, which is conservation of energy in this case. So we need to revert back to the those experimental correlations. Okay, there are a couple of things I want to tell you before we just go through those experimental correlations. Can anyone tell me that if there is a laminar flow and on the other hand we have got a turbulent flow, Nusselt number value would be higher in laminar flow or turbulent flow? Anyone in the class? Anyone?
So for turbulent flow, Nusselt number will be higher
Why is that?
because the length is more.
Length of what?
The flow, the pipe flow.
No, because if you remember how you calculate Reynolds number in pipe flow, that is rho into V mean into diameter divided by mu. So diameter is constant because Reynolds number in case of internal pipe flow, that is not depending upon the length of the pipe. Vinyl, is that clear? It depends upon the diameter. And diameter,
सर जब entrance में
yes. Just a minute, Sharif. Vinyl, is it clear?
Yes, sir.
Okay. So I would tell all of you the reason for that. But let us hear from Sharif. Ji Sharif, what were you saying?
नहीं सर मैं कह रहा था कि जब डेवलप नहीं होता फ्लो बिफोर डेवलपिंग तब तो नसल नंबर हाई होता है हमारे पास टर्बुलेंस की वजह से और उसके बाद वो कम हो
टर्बुलेंस
तो
की वजह से नहीं होता। वो टर्बुलेंस की वजह से नहीं होता। पहली बात मैं आपको बता दूं, वो होता है क्योंकि एच का फार्मूला होता है माइनस के इंटू पार्शल टी बाई पार्शल आर एट आर इज इक्वल टू आर डिवाइडेड बाई टी एस माइनस टी एस, because this gradient is more in the entrance region, so that's why h value is more. ठीक है शारिद, I am telling, I think this is, I
जी
have
सर
told many times, so I would repeat, that is not due to turbulence. It has got nothing to do with the turbulence. The entrance region would be there irrespective that the flow is laminar or turbulent. ठीक है? So that is the entry effect. So that is due to this gradient. Now for the turbulent flow, why as Manahil has rightly pointed out that for the turbulent flow we would be expecting more Nusselt number. It means that the higher heat transfer. What happens there that if there is a laminar flow, the heat which is going to be transferred from these in between the layers of the molecule, that would be only through the molecular oscillations or due to their collision. But in the laminar flow, so in the laminar flow, it would be going through like this, that they are going to oscillate and then there would be heat transfer. But in turbulent, what happens that because there is a random motion and there are eddies. So what does those eddies, we call them eddies, or we also call them vortices. So what does these vortices do? That they pick a molecule from a region where the temperature is very low and throw it at some place where the temperature is more, and vice versa. When this thing happens on a molecular level, so it means that we are getting some kind of translation of motion rather than the heat transfer through molecular collisions only. So in this case, for the turbulent flow, because there is a rapid movement of molecules, they are not staying in their respective positions. They are moving about, so they are going to, of course, they are going to exchange the momentum more rapidly. Okay, so that's why in turbulent flow we would have higher value of Nusselt number. So we can write that Nusselt number value would be quite high. Value will be higher in turbulent flow. Right. So we all know that. Why is that? Because looking at those correlations and applying them, that is not a very difficult thing to do. Maybe if we know that how to apply them, we can do it very easily. But the main thing is to know that why these correlation would produce higher value of Nusselt. Okay, the second concept which I wanted to give, that was that for the laminar flow, friction factor was 64 upon Reynolds number, right? So here you can see that friction factor is only function of Reynolds number for the laminar flow. But when we talk about turbulent flows, F is also function of Reynolds number as well as thickness, that roughness of that surface. Have you heard the name of Moody chart? या फिर Moody chart or Colebrook relations? Have you heard these names? Anyone?
जी सर मूडी चार्ट का सुना हुआ है।
Okay, so
Moody's chart.
okay, so why we need Moody chart? Because when we have got turbulent flow, then we need to cater for the roughness of that pipe. Is that right?
Yes, sir.
Okay.
Yes, sir.
So now tell me that why that surface roughness is not important in laminar flow. Because in the turbulent flows, we know that that is important. So that's why a scientist named Moody developed those chart in 1940. Right? We know that. But why it is not critical for this formula for the laminar flow? Anyone? Because you have got that knowledge. So please enlighten the class. Why it is not important for the laminar flow? Those roughness, surface roughness, because we all know that the any pipe would have more roughness as we continue the motion, continue its operation, like due to sedimentation of something or corrosion or anything. So why it is not important for the laminar flow, that friction factor? Anyone?
तो शायद क्यों उसमें क्योंकि लेमिनर फ्लो में वैसे ही विस्कस फोर्सेस ज्यादा होती हैं
तो टर्बुलेंट फ्लो में नहीं होती?
सर टर्बुलेंट फ्लो में
फ्रिक्शन फैक्टर होता कहाँ पे है? फ्रिक्शन फैक्टर सरफेस पे होगा ना?
जी सर
तो सरफेस के पास तो विस्कोसिटी का इफेक्ट ज्यादा नहीं होता?
जी से ज्यादा होता है मैं कह रहा हूँ लेमिनार में ऑलरेडी विस्कस फोर्सेस डोमिनेट होती हैं तो सरफेस रफनेस शायद ऐसा इफेक्ट ना करती हो लेमिनार फ्लो को
अच्छा, शायद वाली ये क्या मतलब है इसमें? कोई शायद का क्या बात? अच्छा
I'm
चलें,
not sure इसमें
ओके जी, we can discuss. Let's suppose we have got some triangular types of roughness element here. ठीक है, ये हमने उसका zoomed in view देख लिया. ठीक है, whenever we have got laminar flow, in laminar flow what happens that if I draw a velocity profile here at this cross section, that looks like let me choose this like this. ठीक है, उसमें क्या होता है कि inside the boundary layer region the velocity is very low, but when we talk about turbulent flows, for the turbulent flow let me choose red pen. For the turbulent flow, if I draw the velocity profile, that would look like the same, sorry, not the best drawing. I have, okay, just a minute. Let me get this tab stable. So let me draw it. It is kind of this. That in the if you look at the velocity at this point, the velocity maybe for the laminar flow maybe it would be, let's suppose if it is 0.1 meter per second, but for the turbulent flow in the near wall region the velocity is higher. Okay, this addition, so it may be 0.5 meter per second. So why it is very higher velocity for the turbulent flow in the near wall region? Because in the turbulent flow, the particles which are in the core region, they are being thrown near the wall due to those vortices. So that's why this profile look like this for the turbulent flow. Okay, very flat outer region and inner region is very sharp increase. So that's why for the turbulent flows, drag force is very high. ठीक है, very high क्योंकि वहां पे velocity in the near wall region is very high due to that translation of high velocity fluid in this. But in the laminar flow, because in the laminar flow we know that there is no translation inward motion of from the core region, so that's why we have got low velocity, which is 0.1 meter per second. So if it is already less, then there is it doesn't matter if there is surface roughness, because that would decrease it by a little bit. But for the turbulent flow, because the velocity is very high here, so it means that if the velocity would be very high, it would face more resistance, more friction. So that's why for the laminar pipe flow, we usually neglect the role of friction, and we only say that it depends upon the Reynolds number. But for the turbulent flow, as I have explained, that in the near wall region where the surface roughness elements are there, the flow velocity is very high due to that radially outward motion of the fluid due to those eddies, because we have got vortices here which throws the water from the core region near the pipe surface. So that's why the mean velocity in this area would be higher. So that's why we would have very high value of friction factor for the turbulent flow, and drag force would be higher, and then for the same reason we would have high, because then we would have, because h, if I write the h value here, that is again minus k into partial t by partial r at r is equal to r divided by Ts minus Tm. So now because partial T by partial R at R is equal to R would also be very high, because the temperature which is here in the middle would be higher than this. So it means that when the high energy molecules would come here, temperature gradient would also be more. So that's why Nusselt number would also be more in turbulent flow. In turbulent flow. Okay? So this translation of high energy molecules towards the pipe surface, it uh, it basically explains the higher drag force and higher Nusselt number value in case of turbulent flow. Okay, so now we are going to see those correlations, and then we would do one numerical. So I hope that this point is clear to you. So for the, first of all, for the, if we talk about the transitional flow, so for the transitional flow we can say that transitional, or if we still say that we are talking about smooth tubes, that what are smooth tubes, that we have polished it to the machined it to a very fine scale, then for that case friction factor is again only dependent upon Reynolds number. There is no mention of that surface roughness, because we are saying that pipe surface is highly finished. So for that we can use either the first relation when we have got the Reynolds number in this range, or we can use another relation which is Chilton-Colburn relation. So either we can also use no, sorry, this is for the friction factor, and then this friction factor can be used in the here to calculate the Nusselt number if the Reynolds number is in the range of 10,000 to 1 million. Okay, and there is another thing that another friction factor formula can be used. So now this friction factor formula can be used. Either we can use this one or we can use this one. So if we use this formula, which is 0.184 Reynolds number raised to power minus zero point 0.2, then if we put this value here in this relation, 0.184 into 0.125 would be equal to 0.023, and Reynolds number when it would go here because its power is 1, its power is minus zero point 0.2, so it would become Reynolds number 0.8, and this would be Reynolds number 1 by 3 as it is. So usually we use this for the fully developed flow, right? When we have got the Reynolds number is more than 10,000. So if we can also, this is a generic formula which we use, but we can also use more accurate formula for the range of 10 to the power 4, which is 10,000, which is the transitional range basically, 10,000 to 5 million. So it is also covering that the initial portion of the fully developed region, and then going towards this. So you can see that here the formula is a little bit difficult, but it would produce more accurate results for the Nusselt number. And then if we want to include the transitional range as well, transitional range means that from the 3,000 to 10,000 as well, then we need to use this modified formula. So it means that if we have got the fully developed flow, then we have got two options. One is to use this formula, which is Nusselt number is equal to 0.023, Reynolds number this, or either we can use this formula, which would give you more accurate results. So ideally we should use this formula, but even if you use this formula, it would give you acceptable results. And if we have got the Reynolds number less than 10,000 and more than 2,300 or 3,000, then we can use this relation, which is this uh, relation which is given here. Okay, so for the transitional range, we are going to use this second formula. For the fully developed range, we have been given either this, we can use this formula, or we can use this last formula, right? So up till here, we haven't discussed the the uh, we haven't discussed it for the if you see the Prandtl number range is more than 0.5. So it means that we are talking about gases, or we are talking about normal liquids or heavy oil. So for the liquid metal, when the Prandtl number is quite less than zero point 0.5, then if we want to calculate the Nusselt number for those liquid metals, then we need to use these two relations for the which are given here for the turbulent flow, right? So there is nothing to explain very much, because they are empirical correlations, but you can also see that there is kind of a constant value on which something is added due to that. This addition is due to that turbulence effect here, right? In the entrance region, that was due to entrance region, but here it is being added due to the turbulence effect for the constant surface temperature and constant heat flux case. Right. So now we are going to discuss the effect of surface roughness. So for the surface roughness, because you have already studied the Colebrook relation, have you studied this relation in your FM. So for the Colebrook relation, we can use it, if, but the disadvantage of this formula is that it is an implicit formula, because you can see friction factor on the left hand side as well on the right hand side. So it means that we need to have some kind of iterative solution for this. Okay, so that iterative solution, because in 1939 it was not possible very easily. So Moody, a scientist named Moody, uh, he came up with those Moody chart in 1944. So basically, what he did, that he shown the calculation of F from this formula on a graph, okay, which is also available in your fluid mechanics books. So either you use scientific calculators and you can iteratively solve this very easily nowadays. But in 1944 or 1940, it was not possible. So that's why Moody plotted this data on a graph, and then uh, in 1983, another scientist, Haaland, he gave us an explicit relation for the calculation of F. Now you can easily see that the friction factor is only appearing in on the left hand side. There is no friction factor term on the right hand side as it was in the first relation. So whenever I teach SM course, so I usually tell my students to either use this formula, which is the explicit relation. It would because whenever we use those graph, Moody chart, yeah, graph, then that involves that comes comes with the that visual error, which we usually, because that plot is on the logarithmic scale, so that doesn't tell us the exact value. So the best possible route is to use this first relation if you have got scientific calculator. Otherwise you can use this correlation, and if you don't want to use anything, then of course Moody chart is still there. Okay, anything which is not clear here, so that we can do one numerical problem, and then we can kind of discuss the quiz which is going to happen in yesterday's class, in tomorrow's class. Sorry. Okay, ji. So I hope that what you are understanding a portion, or maybe more than a portion of what I teaching you. So now the surface toughness values are given for some plastic, some commercially available pipes, that is given, so that we can calculate F value by putting this epsilon value. Diameter here, diameter is diameter of the pipe, and then we do one numerical problem for this. So now water is to be heated from 15 degree to 65 degree centigrade as it flows through a 3 centimeter diameter, 5 meter long uh, pipe or tube, right? So the tube is equipped with an electric resistance heating. So it generates some volumetric heat on the surface, and because the outer surface is insulated, so all the heat is going to come in to increase the temperature of the water from 15 degree to 65 degree, right? So here it is written that it is insulated, so that's why all the heat which is being produced due to that electric resistance heating, that is going to come in. And then if the system is to provide hot water at a rate of volume flow rate 10 liter per second, which is 10 divided by 1000 meter cube per minute. So that is the volume flow rate. Determine the power required rating of the resistance heating, and determine the surface temperature of the pipe at the exit. So we need to determine two things. One is the power required for that resistance heating. So that power can be just a minute. So that power can be calculated very easily while that because for the power calculation we know because we want to calculate that heat transfer rate, so that is we can calculate q dot is equal to m dot Cp into Te minus Ti. So m dot, that would be equal to rho into volume flow rate. Volume flow rate is given 10 liter per minute, so that would be equal to 10 divided by 1000, which would make it meter cube, and then it is in minutes, so make it in seconds. That would be additionally multiplied by 60. So we would have some value in kg per second. Once we multiply it with rho, so from where rho and Cp value would come? Rho and rho. So sorry. This rho, Cp, K, Prandtl number, mu, these values would be calculated at T bulk, which is the ratio of Ti plus Te divided by 2. So in the problem, if we see that T bulk would be equal to 15 plus 65 divided by 2. So that would be 15 plus 65 divided by 2. So it would be equal to 40 degrees. So at 40 degrees, we would calculate all these fluid properties, right? So once we uh, because now q dot calculation is quite easy. T is known, Ti is known, Cp we can see at bulk mean temperature, and then m dot we can calculate rho into volume flow rate is given. We can convert the units very easily. So now the second thing is, if you see the question, also estimate the surface temperature of the pipe at the exit. Now we need to determine here temperature at the exit plane. So because it is kind of a constant heat flux boundary condition, so first of all we can calculate surface heat flux. So surface heat flux would be equal to q dot, which has been calculated in part A divided by AS. So that would be q divided by pi d into m. Q dot we already calculated in part A. Once we calculate this, now we know that we get the value of Qs from here. Now Q, we know that from the Newton law of cooling, Qs is equal to Ts minus Tn. Right. So now from here, if we want to calculate Ts at the outlet, so that would be equal to just hold it. So that would be equal to uh, T, Ts at exit plane. T here represents the exit plane. That would be equal to Tm at the exit plane plus Qs upon H. Now Qs we have calculated from here. H value we need to determine from the Nusselt number correlation. So TME we know that that is 65. We know that, and because the heat is coming in, Qs would be a positive value, H would be a positive value, so TSE would be greater than 65. How much we need to determine it from the H. So for the H calculation, for this we need Nusselt number correlation. Right. So to determine the Nusselt number correlation, first of all we need to determine Reynolds number, which is rho Vd upon mu, and then once we see that whether that is laminar, turbulent, or transitional, then we can have the Nusselt number correlation accordingly. We can get the value of Nusselt number from the corresponding Nusselt number correlation. So now I have explained you the procedure, that how we are going to proceed. Now we can look at the values. So first of all, we calculate these properties, fluid properties at bulk mean temperature, which is 40 degrees, and then from there we can calculate AC, AS. AC is the cross sectional area, AS is the surface area, and then m dot, that is equal to rho into volume flow rate, which is 0.0 1 meter cube per minute, and then we can divide it by 60 to get it in kg per second. M dot is known, then we can calculate the heat transfer rate to the water, which is the power rating of the heater, which is providing that electric resistance heating. So we can see that it is kind of 34.6 kilowatts. So usually the heater in our home, if we have got electric heater, you can see that setting that is 1 kilowatt, 2 kilowatts. So 2 kilowatt is usually the maximum value, because 2 kilowatt is a lot of electrical energy. So that's why we usually use gas heaters, which are economical. So that's why we avoid those electric heaters usually in our uh, homes and offices. Now, the surface temperature of the tube at any location we want to calculate at the exit plane. TSE would be equal to TME plus Q dot S upon H. As I have explained, this Q dot S can be calculated by dividing this with the surface area. So if we do that, that heat flux value 73.46 kilowatt per meter cube. Then because the mean velocity for the Reynolds number calculation, we need to determine the mean velocity, so that can be calculated from the volume flow rate. And volume flow rate, because Q is equal to AV, we know that volume flow rate is the product of mean velocity and cross sectional area. Then we can calculate Reynolds number. We can easily see that is that 10 more than 10,000. So now we have got a couple of choices. Either we can use this formula 0.023 Reynolds number this, or we can use this formula, because both are applicable. So if you want to be more accurate, then of course we need to use this formula, the second one. But because in the okay, before doing that, we need to calculate the entry length, which is 10 diameter. So 0.3 meter is quite less than the total length of the tube, which is 5 meters. So we can say that it is kind of fully developed flow, fully developed turbulent flow. So fully developed turbulent flow, we can use this formula. Because why we are using it? Because for the in the solution in the book they have used this formula, but we can definitely use the second relation, which is this. It would give you better result, or more. It would give you a result which would match with the real value more closely. Okay, so once we get Nusselt number, then we can of course calculate H from here. K upon D into Nusselt number. H, once we get H, and then we can easily calculate TSE, which would be equal to TME, which is the exit mean temperature 65. So you can see that the surface temperature at the exit of this pipe would be 115. At this location, at the exit, the surface temperature would be 150. So, and that is something which we expect that it would be greater than 65. So you have to do some example problems, A-4, A-6, and then you can also do homework problems. So this is the point. This is the portion of the today's lecture which would be included in the in the quiz tomorrow. Okay, which is going to be take place from chapter number 8, and I have shared the lecture slides already. So I think now we can have a break, and then when I come back, I would give you the introduction for the next chapter, and uh, I would discuss the quiz which you have done, maybe 2 3 quizzes, which the solution of that quizzes, and we would start the proper official start for the heat exchanger design chapter from tomorrow's class, right? So let us take a break of 5 minutes, and then we will discuss it.
Sir?
Okay?
Assalamu alaikum, sir.